Let's get started. So the midterm will be out Thursday morning and it will be due Tuesday. And okay, sorry about that. It's on blank. Okay, and there will be no class on this on that first and two on 3-2. That's a Thursday, right? And on 3-7, 3-9. So this Thursday and next Thursday there are no class. I have like a 12-hour non-stop Zoom meeting on Thursday and Friday next week through NIH, which cannot be moved. So I apologize for that. I will do a makeup class. Most of you can attend it. Some of you cannot. The video will be there as usual. And if the video is not clear, you want to learn something, I will do a special office hour to go over things with you. Apart from this, we are not going to miss any class. So things should be okay. Okay. So, and the graded midterms are here. I recommend in the middle of the class, just come and pick yours. Don't come together, just come at some point. There are too many of you. Thermodynamics used to be 15 students. It's becoming more and more popular, thermodynamics and StatMech, for some reason. So, I mean, Chris Dzerzhinsky's non-equilibrium statistical mechanics has 40 students. I think we are the only place on this planet which has 40 students in advanced StatMech. 10 of them is my group. They all show up together. I don't know why. So okay. So I have not released the midterm key. I'm not going to release, the homework key. I'm not going to release the first homework key because that was just a refresher. The second homework key I would like to release after the midterm. I'm going to repeat one problem from the second homework on the midterm. I'm not going to tell you which one. Okay. So go through everything and think about it because it's going to be repeated. And there is a Slack channel for a reason, so you all can talk to each other. I have not released key, but I'm not stopping you all from discussing. You know, if one of you who has scored full decides to be very generous and release their answer on Slack, I cannot stop you from doing that. So it's up to you all. Okay. Any questions? What? You did okay. You did one mistake. And I can say one thing. So the first problem, last part, has a very simple answer. And most of you got it right, which is the probability that a specific molecule is standing up given total energy. Answer is very simple. I have given you marks just for the answer in this one, but actually you have to work through the proof. So in the midterm, if you don't go through the proof, some of you went through a 1 page of proof, really explaining what's going on. So be detailed in the midterm. I will not be that generous. This is yours. You can pick yours also from here. Okay, so let's get started. So today we are going to talk about grand canonical ensemble. Chandler does this in like one paragraph or as nothing. We will go over it in some detail. Grand canonical ensemble really means if you have a system where there is not just energy being exchanged with the environment, but number of particles is also being exchanged, right? It's a semi-permeable membrane. So it's a very, or just an open container, you know, particles can go in and out. How do we set that up? Even though this is not on the midterm, pay attention in today's class because this is very similar to what we did for canonical. If today's class makes sense, you're in good shape. So we will introduce the grand canonical partition function, which depends on mu, v, and t. We will talk about thermodynamics from grand canonical partition function. And we will, in Tuesday's class, we will talk about averages and fluctuations. So let's get started. So how does this system look like? So we have a box. Inside this box, basically, this is our system. This is something which can exchange number or it can exchange energy with the environment. The environment, once again, we call as a bath, and this we call as a system. And those who came late should watch the video. There was a very important point about the midterm. I basically told you one of the problems on the midterms. Watch the video. So, and total thing, the system plus bath is considered isolated. Okay. So this is to be contrasted. So this is our grand canonical. I don't know why they came up with such strange names, canonical and grand canonical. you can just call it mu v t ensemble. Why mu v t? Because v is fixed here. Okay, so the size of this box of this system is not changing. That is fixed, but it can exchange matter with the environment. And how long does matter exchange take place? Until you reach chemical equilibrium, right? And so chemical potential becomes constant. It can exchange energy with the environment. When does that become reach equilibrium? When temperature is becoming constant, right? That's why mu vt are the control variables. So this can be contrasted with the canonical ensemble, which is, again, the full thing is isolated. The system plus bath is isolated, but here the system can exchange only energy with the bath. Okay, so in this case we had a NVT ensemble. So, and the problem once again is calculating the probability of microstates. So for canonical ensemble, we saw that the probability of a given microstate is proportional to e to the power minus eta b, e to the power minus beta e nu, where, and if you want to get rid of the proportionality constant, it becomes 1 by q e to the power minus beta e nu, where q, which is a function of NVT, is sum over all microstates of e to the power minus beta e nu. And this q contains all possible information of interest, all thermodynamic information that you can care for. So first of all, we showed A is equal to minus kBT ln q. I highly recommend going through this proof. It had some non-trivial physical ideas in order to get this. We assumed equivalence to a microcanonical ensemble in the very large system size in order to do this. And then from this, by doing first derivatives of q, we could get averages of things. By doing second derivatives of q, we could get fluctuations in things. In the homework, you did third derivative of q, you saw the math gets messy, but by differentiating and operating, normally by differentiating log of q, you can get variety of things. Grand canonical is going to look similar. We will have p nu proportional to e to the power minus eta b nu. That term will be common, but now a new term will show up, which is e to the power plus beta mu n nu. Okay, we also have to talk about the probability of a certain number of particles in that microstate. So together, this can be written as e to the power minus beta e nu minus mu and nu. Okay, dimensionally it makes sense. E has the unit of energy, n is dimensionless, or yeah, mu multiplied by n has the dimension of energy, so it makes sense. And if you want to get rid of the proportionality constant, that is going to be 1 by z e to the power minus beta e nu minus mu n nu, where z is known as the grand canonical partition function, so g c p f. And z now depends on mu vt, and this is sum over all microstates of e to the power minus beta e nu minus mu and nu. I'm just writing down the key results. We will work through this and derive these things. But this is the key result.
Why is it that it's positive beta mu and nu?
That's what you will see in the proof. And okay, so log of q gave us Helmholtz energy. Here, log of z mu vt should also give us some thermodynamics. What state function should we expect here? Grand potential, omega g. We did not really talk about it much in 684. We just introduced it once, but that's what's going to come out here. This grand potential actually has a related value, which makes it much more intuitive. Anyone remembers? Grand potential is equal to P multiplied by V. This I'm going to use today, but this is a very good exercise for DIY at home. Y is grand canonical partition function, grand potential equal to PV. We did it last time. The proof was kind of interesting. We used intensive and extensive properties. It was not a trivial proof. Think about it, okay? So this is what we are going to do today. And once again, by differentiating Z with respect to various things, we can get all sorts of averages. In this case, we are allowing the number of particles to fluctuate, right? So we can get the average number of particles. We can get the fluctuation in number of particles. And once again, remember the 1 over square root of n formula? That will show up here also. Arka, you can take your homework. Just periodically keep calling people. Jared? You. Arman is not here. Swimin? Young yeah, other one. Other one. Okay. Kinjal, homework is easy to find. Kinjal, I have deducted 5 points. This is not a stapler. You scored more than 100, so you're fine. Nathan? Other one. Kiet? Aiden is not here. Fahad is on Zoom. Ethan? That's it. I think we covered everyone. Good. So let's proceed further. How do we do this? So the proof for this one is remarkably similar to what we did for canonical partition function. Okay, for a system that can exchange energy with the environment. So let me draw this once again. So we have the outer thing, and inside we have this is our system. This is in contact with a bath. The full thing is microcanonical. And this thing exchanges energy and number. And we are interested in find the probability of finding the system with a certain energy E nu and a certain energy N nu. So once again, we will say that the total number of particles is equal to NB plus N nu, number of particles in bath plus number of particles inside the system. That is constant, right? Because the full thing is isolated. Total energy is equal to EB plus, let me write these things up here. So N is equal to NB plus N nu. E is equal to EB plus E nu. What else should we assume here? Bath is much larger, right? It's Vedant in the Pacific Ocean. It's insignificant. So E nu is going to be much smaller than EB, and nu is going to be much smaller than NB. But it's all about making these approximations at the right stage. If you make the approximation too early, you will be left with 1 is equal to 1. Okay, and you won't be able to do anything. So how did we proceed for the canonical ensemble? We said if the system has a certain state nu, then let's calculate the number of ways the bath can exist, right? So the idea being that if you have the system in a certain energy E nu and a certain number N nu, and if you focus on this energy and this number, then the bath also needs to have fixed energy and fixed number, right? If you focus on one value, then everything becomes microcanonical, right? And this value itself, we can keep changing. So for this particular value, we can look at omega bath, E minus E nu, N minus N nu, right? This omega will be the microcanonical PF for bath. And we will have omega system also, E nu, N nu, but remember later we assumed that omega system is much smaller than omega bath, and therefore it disappeared. We did not care about it. So I'm not going to care about omega system at all this time, okay? Because omega bath is going to be so much larger than omega system. So we are not going to care about omega system. You can work through the proof like we did, and you will see why it later falls off. So the same idea as we did for canonical is that probability, and this is why I said, even though I'm not going to ask you, I can make really hard questions if I put grand canonical on the midterm. It can get really hard, especially you'll get confused which ensemble to use. So I'm not going to ask anything related to grand canonical. On this midterm, N will be a constant, okay? But this proof, you should pay attention to. It will help it's the same idea as we did for canonical. So probability of finding the system in a state nu is defined as P nu. That's going to be proportional to the probability of finding the bath in this particular state divided by that value. So I'm not talking proportionality, I'm writing down the exact value of the probability, omega bath over all possible microstates, right? This is what we did for canonical. In canonical, we also had a little omega system hanging over here, but later we ignored it, right? Because it was so small. So I'm just ignoring omega s if you compare with canonical. So we are going to look at this equation. Let's call this equation number 1. So this is P nu. So what does this mean? This means P nu is proportional to the numerator, right? Because the denominator does not depend on the microstate. The denominator is summed over all microstates. So P nu is proportional to omega b of E minus E nu n minus n nu, right? So let's think about ln P nu. As we progress in statistical mechanics, as we get to real, very interesting parts of StatMech, you will see logs are much nicer than probabilities. Probabilities blow up, right? Probabilities can not blow up, probabilities blow down. Let me put it another way, right? Probabilities can go to 10 to the minus n. But what is log 10 of 10 to the power minus n? 10, right? So log 10 of 10 to the power minus 10 is minus 10, right? So if you are thinking with a probability which equals 10 to the power minus 10, it's such a small number. It won't show up. In fact, you can go and try in MATLAB. Try the following exercise in MATLAB. Type 1 plus 3 plus 2, 1 by 3 plus 2 by 3 minus 3 by 4 minus 1 by 4. And most of the times you will not get 0. It will give you 1e minus 18. Computer 0, right? So with probabilities, you can very quickly run into computer zeros. But if you're working with log of probabilities, you just get a nice, well-behaved minus 10 or minus 18, right? So log of probabilities are very, very useful. So log of, and in fact, in StatMech, the only time, for getting expectation values, you work with probability, but be careful. If you're doing any numerics, you should be working with log of probability. So and we will see that in the later half of the semester. So log of P nu is going to be proportional to log of omega b, E minus E nu, n minus n nu. Let's call this equation 2. Now we will see these assumptions, right? E nu is much smaller than EB, and nu is much smaller than NB. So what should we do next? Taylor series, right? So let me write this down on the next page, this formula once again. So we have ln P nu proportional to ln of omega b of E minus E nu n minus n nu. And where we have E nu much smaller than E and nu much smaller than n. So we can do our Taylor series and write it down as ln P nu is therefore proportional to ln omega b of E comma n, right? This part of the Taylor series, when you just look at the function around which you are doing Taylor series, minus, now the only thing that will be different from canonical, this is a function of 2 variables, right? So the Taylor series, even the first derivative will have 2 terms. This will be partial ln omega b by partial E. What should I multiply with here? Huh? E nu, right? That is the small thing that we are changing. So when you are doing Taylor series f of x plus dx, E nu is your dx here, right? It's the small amount. Minus omega partial ln omega b by partial n at constant EV. What should I multiply here? N nu, right? That is the small thing. And this is what you have to be careful. It's not that E nu or N nu are small. They are small relative to E and N. They are huge numbers, right? So what can I do next? This thing is a constant, right? This does not depend on N nu or E nu. So we can say ln P nu is proportional to some constant. Let's call it C naught. This thing I called C naught. We are not going to care about it in just a moment. What can I say about this ugly looking partial derivative? Has anyone seen this before? But what is this? Thermodynamically, it's beta. Beta of what? Is beta of bath different from beta of system? They are in thermal equilibrium, right? So we made that same assumption right time. This is omega B, so it should be beta bath. But beta bath is the same as beta system at thermal equilibrium. So we don't need to talk about beta bath or beta system. It's beta. Beta multiplied by E nu. This one, what is the second term? And this is where your answers gets happen. The plus comes because this thing is minus beta mu. That goes down to our microcanonical ensemble. Remember when we derived this, it came out to be, and if this is rusty, you should, this is why I said this is important. This is a microcanonical. So in microcanonical, refer microcanonical notes. This thing is going to be plus beta mu multiplied by n mu. And there we go. We have our answer.
In the so when we talked about in thermodynamics, we referred to S and V ensemble, all those stuff. We weren't making any inherent assumption of, because it's at a limit, right? You're looking at a small system.
Yeah.
Yet this seems to agree with what you get for those particular sort of things.
Yeah, that has been done because in microcanonical we introduce the entropy in that way. That's why it's all happening. It's not magic. The entropy is where the magic comes from. We introduced a certain form of entropy.
But it seems to me like you're switching between ensembles quite freely. Like suddenly you're using
In the thermodynamic limit, yes. In the thermodynamic limit. That's why this is thermodynamic limit, right? I'm not talking about omega system by omega n. I moved to omega bath. At no point did I compare omega bath equal to omega system, right? I did not do anything like this. But I'm allowed to say omega is bath or system independent, right? It should be, I see a conundrum. System is a small part of the bath, like yet we are allowed to do that. Yeah, go ahead.
Omega of bath should increase with n because like more particles we have, more states we have. Does it mean that mu will be positive?
Don't ignore the energy. It's a competition. It's a function of two variables. If n and e were independent, then sure. It's subtle. I could easily construct, you should construct some problems where you can see something like this, right? Imagine a complicated DNA or something. Energy is going up. If you keep adding particles, omega keeps going up. But if you add too many particles, the DNA gets blocked into some configuration, right? For example, yeah, actually, we don't need to go to DNA. We need to just look at 687 students. I start putting, all of you are undergoing thermal fluctuations. I add more students, more thermal fluctuations. At some point, I pack the room. What happens to thermal fluctuations? It goes down, right? The number of microstates accessible to you can start going down. So it's complex because it's a function of two things. If dependent only on n, then sure. So you have to be careful. So let's get back to this. So now we have ln p nu proportional to this thing. And therefore, if we take the exponent of both sides, we get p nu is proportional to e to the power minus beta e nu minus mu n nu. Aiden, did you pick up your homework? You picked one homework. Yeah, I didn't notice it. You're sitting on the other side. JP, why are you here? I mean, you are here because you're taking the class. Any questions? Go ahead, Sophia.
I just missed, where does the C naught go? Like, I did not consider it.
Oh, because it's a constant. It's a constant. So let's be more explicit. I would say if I take exponential of both sides, it will be e to the power ln p nu is proportional to e to the power c naught, e to the power minus beta e nu minus mu and nu, right? This thing is just a constant. If you're talking about proportionality, who cares, right? It's a constant. Therefore, and what is this? E to the power ln p nu is p nu. Therefore, p nu is proportional to e to the power minus beta e nu minus mu and nu. Okay. So remember this one. This is the grand canonical probability. Okay, it's just like what you had for canonical, but you have a minus mu, and the minus comes because of how chemical potential depends on entropy. The minus. Why does mu have a minus? It's the integrated first and second law of thermodynamics. That's where it comes from, right? TdS minus PdV plus mu dn. That's where it's really coming from. D is equal to TdS minus mu dV plus PdN. Okay, so this is proportional. If we really want to write down the probability, then let's call this equation number 3. Man, what was my equation number 2? Equation number 2 was ln p nu. We are not going to care about it that much. 3 we are going to care about. So that's equation number 3, which is super important. But we also want the probabilities to sum up to 1. So the exact probability is going to be given by p nu is equal to 1 over z, where z depends on mu vt multiplied by e to the power minus beta e nu minus mu and nu. And this z is essentially related to this e to the power c naught that we ignored, right? So z, in order that the probability sums up to 1, should be equal to summing over all microstates e to the power minus beta e nu minus mu and nu. This is equation number 4, and this is grand canonical partition function. Okay. So let's do just a slight bit of recap. So for micro canonical partition function, what was the micro canonical partition function? Even though very few books use this name, this what just switched to entropy, but that was omega nve, right? Canonical partition function was q of nvt. Grand canonical partition function is z of mu vt, and they are all connected to thermodynamics. Omega nve was connected because kb, well, let me not try to squeeze that in out there. So here we had S is equal to kb ln omega nve. This is something we did not prove. We threw it out there, right? We said define S this way, and look, it's wonderful. It's extensive. It follows all the nice properties you want, right? It followed the constraint principle. We did not prove this. This was a postulate. This was a postulate. We did not prove this. However, given this information, we did show that A is equal to minus kbt ln q of nvt. And now we are going to show that omega g, which is nothing but, actually I missed a sign. Omega g is minus pv. Omega g is equal to minus pv, not plus pv. Omega g is equal to minus pv is minus kbt ln z of mu vt. Okay, so this is what we are going to show next. How do we do this? And why do we care about this? Because if we did not do this, then we don't have a connection between the grand canonical partition function and thermodynamics, right? So we have to do this, then we know how to get all sorts of things out of it. How should we proceed? Any ideas? How did we derive this one for canonical? Anyone remembers?
We looked at ENS.
We looked at E and S, right? We looked at average E, we looked at average S. Let's do a similar thing over here, okay? Let's look at average S. And we need to calculate this average S in the grand canonical partition function. How did we get average S in the canonical partition function? We switched between ensembles. We said, let's assume it's thermodynamic limit, right? And later we went and calculated the fluctuation and showed that it goes as 1 over square root of n. But in order to get this, let's assume, and in fact, all of this business is true only in thermodynamic limit. It becomes more and more, you can use it in finite n, but if you really want to compare it, you have to be in thermodynamics limit, because there is no thermodynamics without thermodynamics limit, right? And it should go to infinity. So let's assume thermodynamics thermodynamic limit. In thermodynamic limit, even though we know that n fluctuates in the grand canonical ensemble, we expect it to be equal to some average value of n, right? We don't know what is that average value. We are going to calculate it in a moment. Right now, we don't need it. We know it's going to be close enough to some average value of n because that's the thermodynamic limit. And I will mathematically show this probably in Tuesday's class. Similarly, E should approach its average value. Thermodynamics should prevail. There should be no fluctuation, right? So what does this mean? If n is becoming constant and E is becoming constant, then it's behaving like a microcanonical ensemble, right? In thermodynamic limit, all ensembles start to look similar. So what does this mean? This means I can use the formula for entropy for the microcanonical ensemble. What is that formula? That is plus KB ln omega. But now instead of NVE, I have to be careful. I'm going to write N bar V E bar. Okay. And I'm going to mark this with a triple star because this is subtle, what we did over here. If you understood canonical, if this is not clear, that means there is something rusty with your understanding of canonical also. Okay, so make sure that this is clear.
We had something, right, that we couldn't explicitly calculate averages in the microcanonical.
Yeah, but which value should we use in the microcanonical? We will use, this is a number, and this number is calculated as the average of the grand canonical. Okay, and we are saying that even though the grand canonical, the number of particles is going to fluctuate as you reach thermodynamic limit, the fluctuations will become tighter and tighter. We saw that for energy in the canonical function. Remember, the standard deviation in canonical, we saw that STD of E by E bar goes as 1 over square root of n. And we are going to see the same thing over here in a moment, that the same thing follows here. And similarly, STD of n by n bar also goes as 1 over square root of n bar. We will see on Tuesday. Okay, so you have to take my word for that right now, that we can do this. So once we have this formula, then comes the next subtle step. So let's call this equation number 5. So now what I can do is to say that now we are in microcanonical mode. Okay, so we have just, this is why it's kind of beautiful. So we have switched gears. In microcanonical, what is the connection between probability and the number of microstates? 1 over, right? So P of E bar, comma N bar is equal to 1 over omega of E bar, comma N bar. Okay. I forgot to number this in my notes, so I'll call it 5A. So put 5A in 5. And again, Chandler does not go through this derivation. Chandler just says you can show it. It's all of this, he says you can show it. That's Chandler. So what does this mean? If you put 5A in 5, what do you get? You get S is equal to minus KB ln P of E bar, comma N bar. Okay. Why did we do this? Why did you do this? You did this because I'm doing it. So you're kind of trapped here. I'm sorry. But think about it. Do we have an expression for P of E bar, comma N bar for grand canonical? We just derived it, right? That's equation number 3. Equation number 3 tells me what is the probability of finding a microstate with a certain energy. So I just need to plug equation 3, which says P nu is equal to 1 over Z e to the power minus beta E nu minus mu N nu, using E nu is equal to E bar and N nu is equal to N bar. If you plug this into the above equation, yeah, go ahead, Tinja.
So this S is equals to minus KB, the law of probability of finding a particular probability of finding average energy and average energy. However, this equation tells the probability of finding a particular microstate.
And what we are saying is that the grand canonical partition ensemble in thermodynamic limit, if you observe it a billion times, it will almost all the time I have to be careful mathematically, not almost all the time. It will be, probabilistically, it will be in that particular microstate. That's the claim I'm making over here. Because of this thing, the standard deviation of n, grand canonical allows n to fluctuate, and it will fluctuate. But as the system size becomes larger and larger, the fluctuations become tighter and tighter. So it's like, okay, you are saying microstate value equal to n bar. It's not going to be n bar, it's going to be slightly different from n bar, but that's like saying billion plus minus 2, right? It does not matter. That's the difference we are talking about.
No, I'm saying that, the probability of finding a microstate is proportional to e to the power minus beta mu minus probability, but the number of microstates can also will also increase, right?
But if you are in microcanonical, this is exact. I have not made any approximation. This is exactly the proof we followed in canonical. Go ahead.
Speaking of approximations, wouldn't be easier to use Gibbs entropy?
You're so tempted. You and Omar, you should gang up on me. No, Gibbs entropy. How do you know Gibbs entropy? How do you know entropy is minus P log P? That's the point.
How do I know it's log P? Because once we say
There is one postulate here. If you go down the pathway, and we will get to Gibbs entropy in a couple of weeks, there is a danger there. Okay, there is a danger. It has led to different forms of statistical mechanics. This is. Look, I'm almost going to sound like a preacher. My postulate better than your postulate, but that's what it is. Okay, there is no fundamental reason. Just like we cannot really compare two religions against each other. This is one postulate. This is the Callan framework. Okay, that's what we are following. So yes, there could be other frameworks, and they can be inspired by using maximum entropy frameworks, and that's one way of thinking. But Kinjal, if this is confusing you, go and see how we did the proof for canonical. It's identical. There is no difference. Go ahead, Omar.
Can we think of a system that has a huge gap in its energy, like say like E0, then the next accessible energy, like for the microstate, is some E1, which is source, and then the average energy is in between. Would it make sense to say omega of E bar and work through, because there's no microstate that
That's a good one. I don't think I have answer right away. Let me think about it. I see your point. You're saying if two things are discrete. I think.
Yeah, I mean for n it's okay.
Send me a message on Slack. Okay, I need to think about that. That's not obvious to me. You're giving me ideas for the midterm. So if you see a hard problem, you know who to blame. We'll get to that. Right now, let's stick with this. So the idea is, once again, even though the energy and n are going to fluctuate, I'm making the claim that on an average, they are going to be the same value. The fluctuations will be smaller. So we can think about it as if it's almost a microcanonical ensemble with this value of n bar, this value of n equal to n bar, and this value of E equal to E bar. So we use the formula for entropy of a microcanonical ensemble. We connect that to the probability, which is 1 over number of microstates. And now we switch gears. We come back to grand canonical. We used this. So compare this side by side to the proof for canonical. It's identical idea. There we did microcanonical and switch gears back to canonical. Here we did microcanonical and we are switching gears back to grand canonical. And we are using this formula for the probability. So let me write down both of the things. So we have, I will repeat it. So we have S bar is equal to minus KB ln P of E bar comma N bar. Yeah, even though you say use Gibbs entropy, this formulation of thermodynamics and statistical mechanics comes from Gibbs. People call it Gibbs entropy, but Gibbs himself did StackMech this way, not the Gibbs entropy way, ironically. So where was I? Yeah, okay. So we have this, and we have just said that we are going to use P of E bar comma N bar is equal to 1 over Z e to the power minus beta E bar minus mu N bar. So let's use these two together. What do we get? We get S bar is equal to minus KB ln of this thing, right? So what is that thing? That is e to the power minus beta E bar minus mu N bar divided by Z. What is that going to be? That is going to be S bar is equal to plus KB ln Z. And then ln of E is nice. It cancels out. What are we left with? We are left with plus KB beta E bar minus mu n bar. So see, something is starting to appear now. So S bar is equal to plus KB ln Z plus KB multiplied by beta. What is beta? Beta is 1 over KBT E bar minus mu n bar. Or S bar is equal to plus KB ln Z plus E bar by T minus mu n bar by T. Multiply both sides with temperature. What do we get? Ts bar is equal to plus KBT ln Z plus E bar minus mu n bar, or minus KBT ln Z is equal to E bar minus Ts bar minus mu n bar. And this is the grand potential. E minus Ts was A bar, right? Minus mu n bar. And this was the definition of our grand potential, omega g. That was a Laurent transform of A, right? Replacing n with mu. That's how we got grand canonical partition function. This is mu Vt. So that's our connection of thermodynamics with grand canonical partition function. And on top of that, you are going to practice at home, because we did it in 684. You can even go and see the video, that omega g is equal to minus pressure times volume. Therefore, this gives a very interesting relation. It looks remarkably simple, is that KBT ln Z of mu Vt is pressure multiplied by volume. That's kind of super cool. Everything disappeared and left with pressure multiplied volume.
Teams.
Oh yeah. Which makes you wonder about LNZ. What if it was an ideal gas then? What would you expect LNZ to be? Something proportional to n, or Z will be e to the power n, right? So think about that. That's interesting, right? In order to get the ideal gas law from this. Any questions? Okay. So this general framework is starting to emerge. The general framework is log of partition function gives you some state function, right? Multiplied by temperature, multiplied by minus whatever it is, but that's the framework, right? Let's call it some, well, KT multiplied by state function is also state function, so I don't care. Some state function. Derivative of log of partition function with respect to some intensive or extensive quantity gives you average of some state function, and double derivative of log of partition function with respect to some internal or external quantity gives you fluctuations of a state function. This is really the framework. All of equilibrium statistical mechanics is contained in this. Now, which partition function are you working with? How do you calculate that partition function? That's where the hard work lies. But the physics is captured here, okay, in these formula. And again, this thing that I drew over here or wrote over here, this is what should be in your cheat sheet in your final exam, this set of formula. On top of it, how do you actually get the quantities out of this? What are the specific expressions for these averages and fluctuations? You can always derive them, but they're kind of gnarly. It takes time to derive them. For example, for grand canonical partition function, we will show next. We already did this for canonical, right? So let's do it for grand canonical. We are going to show that the average number of particles is going to be 1 over beta partial derivative of log Z by partial chemical potential at constant volume and beta. Okay. We are then going to show average energy is going to be minus partial ln Z by partial beta at constant mu V plus a mu N bar. That's the formula for E bar. So you can see it's hard to remember. If you don't remember this, you can derive it in 2-3 lines, but it's kind of hard. So it's best to, I can never. Do you still remember the natural variable for H? See, he can remember this. No one else. And P bar is equal to plus 1 over beta partial ln Z by partial V at constant mu beta. We are going to show these three. In fact, this I'm going to show, and these you're going to do at home. This will be on your next homework, which is homework 3. Even though it's grand canonical, I recommend practicing it. This is good practice for your midterm. Okay, the problems on the midterms will be similar things, differentiating partition functions. It won't be grand canonical partition function, but it will be canonical in the same idea, working and how to calculate things. So work through these things, and I'm almost certainly going to put it on your homework 3. So let's look at the first one, and the proof for the second two, other two are very, very similar. So let's try to calculate N bar. And yeah, and I want to remind once again that mean thermodynamic quantities depend on the first derivative of partition function, second term, and fluctuation of thermodynamic properties depend on second derivative of partition functions. So we have to calculate N bar. How should we proceed? Someone who has not answered. Nathan already told me natural variables of H. Vanessa, what do you think? What formula should I write next? I'll give you a small hint. What should I sum over? All microstates, right? To calculate the average of anything in statistical mechanics, I go to every microstate, correct? And in that microstate, I will look at the value of N. And then I will have to multiply it with something. So question for Vanessa, what should I multiply it with in that microstate? You can go through your notes. It's really basic. Think about.
Yeah, I was just thinking the e to the minus beta.
Correct, but even simpler, the probability of that microstate, correct? The e to the power. So see, this is the thing. You're getting trapped because that formula is, you're just seeing it, right? It's hard to remember, but it's just the probability of that microstate, right? So you go to every microstate, you calculate the value of that observable in that microstate, and you multiply it with the probability of that microstate. Okay, thanks. You're off the hook. So now we can say what Vanessa was saying is to nu and write down the value of P nu because we just calculated it, right? P nu is e to the power minus beta E nu minus mu N nu divided by Z. Okay, so this becomes 1 by Z nu N nu e to the power minus beta E nu minus mu N nu, right? What should we do next? It's going to look like a bizarre bunch of algebra, but just stay with me and every step will individually make sense, or you'll be like, how do you know how to do that? I don't know. That's how these StatMech proofs work, and you have to work through it a few times to get intuition. So in order to go where we want to go, what we are going to do is to keep it this way and multiply, divide by beta. We can do that, right? Beta divided by beta is 1. Summation mu N nu e to the power minus beta N nu e to the power plus beta mu N nu. Okay. Let's keep the denominator beta outside. Let's bring it this way. Okay, this one we keep outside and this we take inside. And then it looks like beta n nu multiplied by e to the power minus beta e nu e to the power plus beta n nu multiplied by mu. Now, stare at this one for a moment and see what we have done here. We wrote this in this form for a particular reason. Why did we do this? Because d by dx of e to the power kx is equal to k e to the power kx, right? That's what we are trying to use. That is what is there in these derivations. You have also to think about this form. So what are we differentiating this with respect to? We can differentiate it with respect to e nu. If we differentiate it with respect to e nu, we would get minus beta. So that's not sufficient. But if we differentiated this product with respect to mu, we would get this thing, right? So this thing is 1 over z beta. And you did exactly same derivations for canonical. It's the same idea. Partial by partial mu of this whole thing. Why could we do this whole thing? Because this one does not depend on mu. There is no dependence, right? Why is that useful? Because now the partial with respect to mu can be brought outside the summation. Sum of derivatives is derivative of sum. So this is 1 over z beta partial by partial mu summation over microstate e to the power minus beta e nu minus mu and nu. Question next for Swimin. Where is Swimin? She's in the back. Oh, I can see you. What is this thing in the box? Have we seen this before? That's z, right? That's the grand canonical partition function. So what did we just get? We got n bar is equal to 1 by z beta partial by partial mu of z, right? It all disappeared. So what are we left with? We are left with n bar is equal to partial 1 over beta partial ln z by partial mu. That's what we wanted to prove. Okay. So it's one page of algebra. It's kind of try to do it yourself, closing the book. It's good practice even for the canonical partition function because it's the same idea. There is nothing very different here. And on top of that, these I'm not going to do in class. It's the same exact proof. For E bar, you will not start with N bar is equal to Nu P nu. You will start with E bar is equal to summation E nu P nu, right? And then you will do the same business of saying what should you differentiate in order to get that, and you will get everything. So work through it. Any questions about this? So we just showed that the average number of particles is related to the partial derivative of log z with respect to mu. And we could have expected this. If you go and think about, you could have written this down in a, yeah, go ahead.
Wouldn't it be similar to sum over n and probability of number of states?
It's the same thing. The nu itself is a compilation of E and N. Here, E is not doing much. It's the same thing. It's the same proof. Could there be another way of deriving this equation? By appealing to thermodynamics. No, derivative of the grand canonical partition function. Sorry, derivative of the grand potential with respect to mu. That would have given us something similar, right? So this is for something to think about because I don't know whether it's correct or not because it just came in my head. So if we had done n is equal to, so what is the connection between, so what am I trying to say here? I'm saying that so omega g is minus kt ln z. So if I go to this formula where I wrote n bar is equal to 1 over beta partial ln z by partial mu, And if I use omega g is equal to minus kt ln z, and if I substitute n bar with n, would I get an equivalent relation in thermodynamics? Huh?
Yes.
We should. If we didn't, then there is some problem, right? So again, check. But that doesn't prove that even if we could derive, and I'm sure we could derive something like this, but that wouldn't talk about the average value of n. Here we have a nice relation for the average value of n. So I'm going to stop here because you guys also have an exam and I don't want to bombard you with too much information. But the point today is we talked about this probability in a grand canonical partition function. The relation is, you will remember, it's a different sign between beta and mu. It connects to the grand potential function. I gave you a couple of things to practice, which will be good for your midterm. I think it will just get the gears going. Of course, you could be in the school of thought that you will practice after seeing the midterm exam and practice on the fly. That's fine if that's what you want to do. And I also said one of the second homework problems will be on the midterm with a very high probability. It does not mean it will definitely be there. It's very likely to be there. 95% likely, okay? So if I teach this course 20 years, this is my 6th time teaching it, one time I will be wrong. Is it this time? I don't know. We have to be ergodic, right? So do that. So, and these also you should do at home. This is for grand canonical, but it will be helpful for you to become familiar with this type of manipulation. Next time, what we are going to do is to show that we will calculate the standard deviation of n, and we will show that standard deviation of n divided by n bar once again goes as 1 over square root of n. And if you're feeling really excited and brave, try doing it yourself and you will see it comes out nicely, which means once again that even though n is fluctuating, it takes, the fluctuations become less relevant as n increases, which then is justification of how we derived our connection with thermodynamics by using this formula, right? This will be our justification of this in the thermodynamic limit. Okay, otherwise the exam will be out Thursday morning, 6 or 7 a.m., something like that. It will have a few problems. I don't know how many. It will be fun, type 2 fun. And it will be due on Tuesday, and no class this Thursday, no class next Thursday. We will be doing class on Tuesday. And there will be a makeup class on 13th March in the evening. I know four of you cannot make it. So a couple of you already wrote to me that you're okay with that. So a couple of you might not be okay with that. I totally understand it. It's my fault that I have to do something like this and you are not expected to have free time then. So if you really cannot make it and if the video is not your satisfaction, I will do a separate office hour and work through you. After you have watched the videos and something is not clear, we will do a special office hour to work through things. Okay, so good luck with the midterm. It will be fun.